So in this video we're going to look at a question based on the hyperboloid of revolution that I've created for our DCG portfolio. So firstly, let's look at the question. So our question says a monument has been proposed for O'Connell Street in Limerick. The monument is based on a truncated hyperboloid of revolution. So we have three parts, A, B and C. So firstly, if you look at part A, we can see it says construct a plan view and elevation of the monument prior to it being truncated using the rectangle method. Part B, determine the true shape of the surface LK once the document is truncated and complete the relevant views. And then part C says using notes and sketches outline the key principles related to a hyperboloid of revolution. So if you look at the question here, we can see our image of our monument proposed for O'Connell Street in Limerick. And we can also see our hyperboloid of revolution with our cutting plane here. Now our dimensions given, our base circle is going to be a diameter of 60, our throat circle will be a diameter of 30, our cutting plane will be 40 degrees from the top of the hyperboloid of revolution, and our overall height is going to be 100. So that means that our throat circle will be 50 high. So our solution will be placed here on the right hand side. So let's begin into this. So given our measurements, we can firstly draw in the plan view of our base circle and of our throat circle, okay? We can then project up our center line here, and as we know the height of our throat circle and the width, we can draw in our throat circle. So the first step then to create our hyperboloid of revolution is to start drawing in some construction lines. So I have these lines layered here. So firstly, if I turn on construction, we want to create some rectangles. So these rectangles are going to be made so we can create a double hyperbola on either side of our center line. So firstly, we're going to bring up our yellow lines here, which will give us our widths. So we know that the points on each side of our throat circle will give us two vertices. So we'll have vertex 1 here and vertex 2. So if we project up these widths, then on our center line here, we're going to get vertex 1 on the left and vertex 2 on the right. By drawing across our center line to the outside of our rectangles, then it'll allow us to get a rectangle here on the top left, top right, and bottom right. And these are the four rectangles that we're going to be dealing with in relation to creating our hyperboloid of revolution. So how you go about creating this is, let's focus on this rectangle up here in the top left first. So we're going to divide both our left side and our top side of the rectangle into equal divisions. So this is a width of 15. So we're going to divide this into 5 equal segments of 3. This is a height of 50, so we're going to divide this side into 5 equal segments of 10. So I'll turn on the layer of our rectangle method now, and we'll be able to see clearly how this method works. Okay, so like I was saying here, we're going to divide this up into 5 equal segments, and we're going to divide our left side up into 5 equal segments. Now once we have this done, we want to join it to our two vertices. So our top points are going to join down to vertex 1, and our points on the left are going to join over to vertex 2. Now where these lines intersect are going to give us points. So if I turn on our point layer, we can see here where line 1 from our top intersects line 1 from the left hand side of the rectangle will give us a point. Similarly, line 2 here intersects with line 2 from the left. This will give us another point. Line 3 from the top intersects with line 3 from the left, and we get another point. And the same with line 4 and line 4 intersect to give us this point here. So once we have these points found, we can draw one section of our hyperboloid of revolution. Now this process is going to be the exact same for each rectangle in this construction. So you can just follow the same process the whole way around. These will give you points in each rectangle, and ultimately you'll be able to draw your hyperboloid of revolution. So we can turn on our hyperboloid layer here, and we can see that our hyperboloid of revolution is drawn in the whole way around. Now I created this in SolidWorks, so simply I was able to create one section of the hyperboloid of revolution and then mirror it about both axes. and this then just saves time in drawing in the hyperboloid of revolution. So what I'm going to do now is just turn off those construction layers again and make it easier to see our next step. And we're going to turn on our cutting plane. So we can see here that the cutting plane LK, like we talked about in the question. So we want to find the true shape of the surface along here after our hyperboloid is truncated. So how we're going to go about this is by inserting some horizontal cutting planes. So our two most extreme points of our cutting plane are both here and here. So we want to insert some horizontal cutting planes that are going to go across here and intersect our horizontal cutting plane. Our horizontal cutting plane will intersect this cutting plane at different points. So if we turn on our horizontal cutting plane layer here, we can see that, like I was saying, we're going to insert horizontal cutting planes going across here. So we have 1, 2, and 3. So once we insert these, we want to draw them in plan. So how we do this is we take the distance from our center line here, so from our axis to the point where our horizontal cutting plane meets our hyperboloid, and this is going to give us a radius. So we can then bring this down and draw it in plan. So taking radius 1, radius 2, and radius 3, we can draw in circle 1, circle 2, and circle 3 in plan. So the next step is where our horizontal cutting planes intersect our cutting plane LK here are going to give us points. So we can see cutting plane 1 intersects at this point here, cutting plane 2 at this point here, and cutting plane 3 intersects at this point here. So we can then project down all of these lines. We're just going to follow one, for example, here. So if we look at cutting plane 1 and where it's intersected, we can follow this line down. And we can see that where this line intersects with our circle 1 in plan is going to give us 2 points. Similarly, for cutting plane 2, it intersects our circle 2 in plan at 2 points, and cutting plane 3 will intersect at 2 points. So we also want to bring down our two most extreme points. So we can see this point here is going to be on the very extreme of our circle, and this point here is, when we bring it down, is going to give us a point here. So now once we draw in this, what we can do is join up these points to give us our cut surface in plan. So if we turn on the layer of our ellipse, we can see that once all of these points are projected to plan and joined up, it's going to give us our true shape of the cut surface in plan view. So now we want to project our true shape of the cut surface here. And what we need to do this is use an auxiliary view. So we can see I've just turned on the layer, so that's going to be our true shape of the cut surface. And what we want to do is figure out now how we're going to go about actually finding this. So we have all of these points in elevation here that we found. So we have point 1, point 2, point 3, point 4, and point 5 here up in the top right corner. So what we can do is bring lines from all of these points up perpendicular to our cutting plane LK. So if I turn on our light blue layer here, we can see that all of these points are projected up perpendicular, so at 90 degrees to our cutting plane LK. Now once you have these points projected up, we can draw in an x2, y2 line. So if we turn on our layer x2, y2 up here, we can see that this x2, y2 is going to be now perpendicular to our blue construction lines, and it's going to be parallel to our cutting plane LK here. So once we have these lines drawn, we want to figure out how we're actually going to find the widths in order to draw in our true shape of our ellipse. So if I just turn off the ellipse layer for 1 second again, so we're just left with lines here and we don't know the widths. So in order to find these widths, we go back 2 steps always for our auxiliary views. So back 1 step is back to our elevation, and back 2 steps is back to our plan view. So we're going to take our widths from plan. So we have some widths here. We have width 1 between this point here and this point here, width 2 between these 2 points on our circle 2, and width 3 between these 2 points on our circle 3. So if we follow these lines up, we can see this line will be our blue line here. So what we want to do is use that width then to find points on our ellipse in our auxiliary view. So we can take, say, from our center line here in the circle to one of the points, and this will give us half of the width that we need. So we can then step off half of this width here, and this will give us a point in our ellipse. Similarly, for the rest of the lines, we can step off from our center line here to this point here will give us another width. So if we step off this width here, it'll give us another point, and the same for point 3. Now, simply when you're drawing this, you're just going to step off the width on the other side as well, and this will give you the points. So the way I did this is I just drew in one side of an ellipse around here, and then I was able to mirror it around this center line. So if we draw in our ellipse again, we can see that you simply just join up all of these points then using our widths that we have found in plan view, and this will allow us to draw in the true shape. So we've satisfied part A and part B now. Part C, using notes and sketches, outline the key principles of a hyperboloid of revolution. So these key principles you'll see in the PowerPoint. I've created a principle sheet, which I think include most of the key principles in relation to the hyperboloid of revolution. So if we turn on all of our layers here now again, we'll be able to see our full solution. Okay, so we can see here, so firstly, using our rectangle method, we were able to construct our hyperboloid of revolution. What we did then was inserted horizontal cutting planes in elevation and brought these widths down to plan. These give us radius to draw in our circles in plan. Then when we brought down our intersection points here, these gave us points in plan, which allowed us to draw in our ellipse in plan here. Once the ellipse is found in plan, you're going to project an auxiliary view from your cutting plane in elevation, and then we can use our widths here that we have in plan view, transfer them up here, and this will allow us to draw our auxiliary view, which will in turn give us the true shape of the cut surface. So that with our full solution there, that is how you go about finding, firstly, a hyperboloid of revolution using the rectangle method, and then secondly, using an auxiliary view to find the true shape of the cut surface.